It's my absolute pleasure to welcome you to Investec this morning for our technology teach-in. You probably know that in March 2021 we raised £180 million, and in the summer of that year we had a technology teach-in, sadly virtually, where we described how we were intending to deploy 100 million of those funds towards electrolysis. And so we're back today to describe how that process is going, and we really hope you enjoy today's session.
Thanks, Elizabeth, and welcome everybody. It really is a pleasure to be here face to face after having done several of these online. When I was 18, I was lucky enough to get a scholarship from ICI in Runcorn. The weird thing is, I left that industry in 2001 for something I thought was going to be more exciting. I thought the chemical industry was going nowhere. It wasn't a growth industry. It wasn't very exciting, and I went off and did an MBA, and then I got into the exciting world of fuel cells. I didn't think that 20 odd years later I'd be back talking about electrolysis. There's a lot of hype about hydrogen. It's been around a long time, but it's interesting in terms of why is it now? For me, almost 30 years later, this is so important. If you believe in a 1.5 degree future, we need about 600 million tons of the stuff by 2050. I think that industry and governments are very committed to these kind of targets and putting big money behind that. And at Ceres, we are very well placed to play in this global opportunity. So don't think of it as something to be feared. Think of it as something that you should grasp. Why we took the decision to also go into green hydrogen electrolysis 2 years ago is because the fundamentals of solid oxide mean that there's a big advantage for industrial decarbonisation. And for me personally, I think that's the real part of this market analysis, as in I don't think you can really dispute that's going to be where you're going to see hydrogen deployed to begin with, because it's already where it is today. If you take a high temperature solid oxide electrolyser and you compare it with a low temperature, a PEM or an alkali, best in class there, they would need 50 kilowatt hours per kilo of hydrogen. So 50 kilowatt hours of electricity to give you a kilo of hydrogen. With a high temperature solid oxide, that number reduces to 37. And that's because you can utilise the waste heat from industrial processes directly, and it therefore gives you this 26% efficiency. So 26% better OPEX and 26% reduction in the CAPEX. And what does that mean? So if you take 1 million tonnes, and I think this is sometimes overlooked, to produce that with a low temperature electrolyser solution, you'd need 6.3 gigawatts. To produce that with a high temperature, you'd need only 4.7. In terms of the upstream renewables, for low temperature, you'd need 12 gigawatts, whereas for high temperature, you'd only need 9. So think of it very simply. That's instead of 12 wind turbines, you'd need 9 wind turbines. Those kind of investments around the whole infrastructure is often overlooked, I think, by investors who say, well, how much is your CapEx going to be, etc. This is really important stuff in terms of then you can drive towards a low levelized cost of hydrogen, and that enables you to decarbonize some of these industries that we're going to talk about this morning. We have to maintain technology leadership. The reason that Ceres is a preferred partner to some world-class organizations is they can't get this technology anywhere else. Now, we have a clear, highly differentiated technology, but we have to maintain that technology advantage to operate a licensing business. Otherwise, in 5 or 10 years' time, we're no longer relevant. So we are spending most of our time, of our 600 people, on the core development of technology and its application in the manufacturing side. We're not ourselves building plants, we enable people to build plants, but our focus is all about the next generations of technology. We're now going to go a bit deeper into the technology side. I'm going to hand over to Caroline Hargrove, our CTO, to kick us off.
Good morning, everyone. As Phil said, I joined as CTO about 18 months ago at Ceres, but before that I was 3 years on the board. And when the opportunity came to join the team full time and to work on this tech that has a potential to have a really real impact on climate change and work with this team, I was so excited. I spent my first 20 years of my career working in McLaren. I'm an engineer, and I develop models, simulation, AI, in a dark room, very unglamorous actually, to develop what often we call now digital twins. And I know you might think, yeah, this is bread and butter these days. If you go back 20 odd years, there was a lot of skeptics that did not believe that doing this would be of any use. Luckily for us, we had a young Lewis Hamilton, and when I say young, he was an aspirational F1 driver. That was before he became our main driver. And his dad used to drive him because he didn't even have a license to drive on the road. Now, just to give you an idea of when we started on this journey. But the point is that it became a tool that we used all the time because we needed to get a feel for how do we project whether an idea will be good. You never actually built a part for a car unless it was first driven in a simulator. We're not finished because we have to keep on doing our R&D, and especially in the electrolysis side, there's more to come. And we will keep innovating because that's in our DNA. You'll understand that if you're actually a technology company, we also have to protect what we do. And you'll see that it is a lovely hockey stick in 2018. And that shows why our business model works. Because from 2018 onwards, we started working closely with our partners. What we're learning from them, we're harvesting the IP, going back to our core technology, and we can then also license that to others. So our P portfolio looks really nice. And just to reassure you, in 2021, we haven't just stopped. It's just that these are published patents. That hockey stick, if anything, is actually steeper today. But if you put a stand on test today and you want to see whether it'll last 10 years, you'll have to wait 10 years. That's not very fast innovation, I hear you say, and you're totally right. So what do you think we're going to do? Well, we have no option but to do digitalization, modeling, simulation. And this is what we're investing a lot of effort in. Because not only do we need that to be able to have products that will last and understand that they will last and have confidence that they will, our partners need that too. They need to build systems faster and reliably, and they rely on our simulations to do that. And that digitalization and the AI that we put behind us is crucial. And you can see that, even though we did this in Formula One and that was great because you have a car that goes faster, we need this to save our planet. We need to take risk today, and the only way we'll do this is by investing in our simulation capacity, and we are. And I can also say that some of the AI that we're using is not just going to be useful to our designs and our processes, but actually we're starting to plant seed into using AI to develop new materials. I will now hand you over to Julie.
Thank you, Caroline. What I'll do is I'll take you a little more deeper into our technology and our technology in general. And at times you'll feel like it's back in your chemistry class or your electrochemistry class. And if you had a bad experience in those classes, forgive me, but I'll try to make it a little more exciting for you. So that's the metal support. We have about a 300 micron of low-cost ferritic steel on which we put our ceramic layers. And it's like a coating of ceramics on that. So overall, it's very, very cost effective. But the main ingredient, like we said, is ceria. And ceria is something that's very low cost, very much available, even though it's called a rare earth metal. And just to give you an example, other technologies of fuel cells use platinum. We are way low cost than anything like platinum or iridium or nickel. So it is a very exciting technology because it doesn't use any precious metals. It's got very conventional metals, and it is extremely robust and very easily manufacturable. The other thing to mention is because of our lower temperature, we can use automotive type gaskets in our stacks. So it allows for using metals and gaskets which are already being developed for other products, for example. And that allows us to do lots of good on-off cycling, keep the cost low, keep supply chains that are already existing. So those are some huge cost benefits and sustainable material benefits of our technology. On the fuel cell side, you produce heat when you make power, and you want to reduce the amount of heat. But on the electrolysis side, the heat is actually good. You need electricity and heat to produce your hydrogen. And both of those together gives you that high efficiency that we just talked about. So it's a win-win trying to get that. And then this shows that I talked to you about the thermoneutral voltage. We can run our stacks at the thermoneutral voltage. And this shows steady state, running them with almost no degradation. So like I said, we have very good, and we do a lot of this in R&D, run them and see how they do. And basically, you get very good, and these are the things that we're using then to scale up and put them in big stacks and systems and run them. Before I hand it over to John, I just want to say, I was just in the US last week, and we gave our talk on where we are. And I've been doing this for so long, but I have never seen the excitement I saw in that room. So with that, I'll hand it over to John.
Thank you, Shubi, and good morning, everyone. We built our first electrolyzer cell module prototype. So this is 8 of our B5 stacks inside. We built that and got that on test just before Christmas last year. We were really excited to get to that point, but we were even more excited by the performance that we saw with this electrolysis cell module. It produced a really compelling module efficiency. So at the module boundary, it was 38 kilowatt hours per kilogram hydrogen, which is pretty much world class, to be honest. Now, this is supplied with steam at 150 degrees centigrade. As Shubi mentioned, you require steam to get to those efficiency levels. But even so, this was a really great step forward. Since that time, we've now tested a further 5 of these modules, because these modules are going to end up in our demonstration system. We're moving at pace to get them tested. They've all shown very consistent and compelling performance, which we're really proud about. It's really testament, I think, to the engineering expertise and capabilities at Ceres for scale up. So just to touch on what the roadmap kind of looks like from where we are today to first commercial deployments over a sort of 5-year time frame. So really there's 3 main lanes of the roadmap. The first one I've been describing to you this morning is the technology evaluation lane, where we're taking the technology, we're building prototypes, we're building demonstration systems, and we're operating those pilots with partners to really learn about the technology operating at scale at a relevant context. The second lane is delivering the stack technology from where it is today to a dedicated and optimized stack product for SOEC operation. And this is really an evolution of where we are today. So we're shortly going to be releasing a new product release for our FC applications, and the EC application is really going to be an evolution of that. So no massive design changes at all. It's going to be building on the knowledge in FC mode with some optimizations for EC mode. And then the third lane is really, it's the commercial deployment, those commercial engagements with partners who wish to take what we have, the core technology, the system reference designs, the information and data from the demonstration systems, and start to build all of that into products that can be deployed at multi-megawatt scale to green hydrogen projects. And we see that operated, working in a couple of stages. The first one is coming up with a reference design, and then releasing those products at beta stage, and then moving those products into first commercial deployments. Being in the electrolyzer business, we're always asked, what's your product look like and where can I buy it? So we do have to explain that we're a licensing business, and we're not going to be making products, and that's for our partners to do. But I think it's always helpful to have some sort of vision about, what could a product look like if we put Ceres technology inside? So here's one idea around that. It's a 20-foot shipping container footprint, just to provide you with a sense of scale. We've got 6 12-stack arrays in here. And what we're doing with the stacks is threefold, really. We're increasing the active area. We're putting more cells in the stack for the next release of stacks. But we're also pushing current density up somewhat. Also in this module, we've simplified it greatly. So as I said before, we don't need a lot of the systems which are in the demonstration system for a commercial product. It can actually be quite a simple proposition. So to that end, we see that we can get on a 20-foot shipping container footprint somewhere between 2 and 3 megawatt power input, or 1.2 to 1.8 tons per day of hydrogen output. It's clear that the efficiency benefit of solid oxide technology has not only reduces your energy bill, your electricity bill on an annual basis, but it really does reduce the amount of electrolyzer capacity that you need, and as Phil mentioned, the renewables infrastructure as well. So it's not only the amount of electrolyzers themselves, but the power electronics, which aren't cheap. So the power transmission infrastructure, the land use, the footprint, the whole size of the proposition comes down for the same amount of hydrogen output. So I think it is worth considering all these aspects in the round when looking at using this technology for potential green hydrogen projects.
Thank you, everyone, for indulging my participation remotely, dialing in from Canada today. If we look at the hydrogen value chain specifically, our approach to the market is to try and ensure that the value chain all the way to the end user is enabled to accelerate our path for the Ceres technology to the end use case. The water through progression, just to share, typically there's a joint engineering program that we procure. Often that's 2 to 3 years. We help our partners practice our intellectual property. We don't just license patents and let people get on with it. We actually help them succeed with our license, and we actively participate in that. And then once the product is developed and embodied, there's obviously a supply consideration. Those partners can either supply themselves by procuring a manufacturing license to the cells and stacks, or in theory, they could buy stacks from one of our existing licensees. And once those factories come online and are fully servicing that demand, we obviously extract the royalties per kilowatt, and every market that someone is servicing is another bet we're placing on a growth opportunity for our company. If the product does extremely well, our royalties grow. And we are looking at multiple applications, as you know, and multiple bets. So we're hedging our future revenues through this partner acquisition process. And what that means, the engineering services and licensing fees are the sort of purple, magenta line. And we actually see that our 600 people are approximately right-sized for servicing the partner acquisition today. We don't see that we need to grow our operating costs significantly to continue our growth story. What we're looking forward to is when the factories come online starting next year, that the growth in our revenue starts being driven by royalties from the factories that are delivering products, and we can efficiently digest new partners with a lot of the cost base that we had. And that's an exciting time for us because it's a time where our revenues grow, our margins become quite healthy, and the more partners we have, the more bets we're placing on future royalty opportunities for the company. And we believe that we have very strong partners in Bosch and Doosan, Weichai, and obviously we're procuring several more along the way to enhance this revenue story.
I want to thank everyone at Ceres, all the work that you've done over the years in bringing the technology to what it is now. So thank you.
Our technology is very differentiated from what's out there, and it is really exciting to be able to explain that. And when people get that, you basically feel the excitement in the room. For us who have been through this and have been doing it every day, and we wake up in the morning excited about it, it's great to get that feeling also from our investors and all the other people who are here today.
We've had a fantastic event here today at Investec. We covered our ambition to have multi-gigawatts of capacity of Ceres technology in production by the end of the decade. That's all about enabling our partners to succeed, our commercial scale-up, and also maintaining our technology leadership. It's not often that you get a chance to spend a few hours with potential investors and do a deep dive into the technology and talk about the scale-up of these technologies. And it's so important because we need this backing if we're going to achieve net zero and scale Ceres into the world-class company we want it to be.